Okay, October 15th in the porch of Ray Tomes, and we're going to learn about the five senses.
Yeah. So, everything we know through our senses.
Yes.
Through our sight, through our hearing, through smell and taste and touch. We might say that some of the things we know now, these days, we get through radio or X-rays or through magnetic things that our instruments do. But we can only know about those, again, through our senses. We can observe what's happening with those. We can see them as an extension to our senses.
Yep.
But ultimately, it has to come into our senses or we don't get it. So I want to talk a little bit about those in relation to frequency. So we have the light. We see a range of colours on the spectrum, and it's quite a look around us. There's all sorts of colours everywhere.
Yeah.
But we have to understand that's only one octave. There's the frequency ratio 1 to 2 between the lowest frequency we see and the highest frequency we see. And they're very, very high frequencies, the frequencies of light. But the spectrum of electromagnetic radiation that light is a part of continues on away in that direction and away in that direction. The radio waves are much slower oscillations than light. We have infrared beyond light, and then so on and on through the radio waves. And the other way, we have ultraviolet, and we have X-rays, and we have gamma rays, up to a huge frequencies. And so there's this massive spectrum of which we just see this teensy little bit.
Yeah.
And we've made instruments that can look beyond that and extend that. When it comes to sound, we hear a wider range there. We hear from about 20 cycles per second through to about 20,000. As we get older, that's come down a bit. And those, 1,000 to 1 ratio instead of just 2 to 1. But of course there are sounds beyond that. Animals like whales and elephants use much lower sounds. Dogs hear higher sounds.
Yeah.
Insects buzzing around at sounds we can,
Yeah.
way up there. So those, there's that big spectrum there as well,
Yeah.
which we hear more of. But they're all oscillations. Light is an oscillation of the electromagnetic spectrum. Sound is pressure waves in the air,
Yes.
and then in our head. The same is true of smell. Smell is based on little tiny hair-like things that are in our nose, and each one is like a little tuning fork. And when it's hit, it vibrates at a particular frequency. If it happens to come into contact with a molecule, every molecule has different frequencies it vibrates at, and the frequencies may be due to some way that it expands and contracts something, or some way that it twists, backs and forwards, and various different motions that it can do. Each molecule may have multiple different frequencies in it. Just like if we make some physical thing and hit it, it may make multiple different frequencies. Those frequencies it's got, if a molecule, some molecule comes in touch with one of these little hair-like things, and this happens to have the same frequency as that, then it will really get it buzzing.
Yeah.
It's a singer in the wine glass thing again, it's a resonance.
Resonance.
Each of these hairs is capable of picking up, there's lots and lots of different ones with many different frequencies, and they're capable of picking up all the different vibration rates that molecules have that may be of interest to us for some reason or another. Smells to attract you, or smells to keep away from.
So light is electromagnetic oscillations, sound is oscillations in the air, and smell is molecular, causing vibrations with our receptors.
Yeah, and so those vibrations are so fast, the signals from those can't be sent directly to the brain. The brain couldn't cope with it. So it actually has a means of, for each one, it makes a different frequency to send to the brain, which is a much lower frequency than the one that the
modulates.
Vibration was. Yeah. Well, it modulates. It translates into a different set of codes, and those arrive. And any one thing that we smell often has multiple different frequencies associated with it, and we pick it up on different things. When they make some of these scents for perfumes and that, they whack a whole bunch of interesting ones, and you go, ooh. So that's what's going on with those. Taste is a chemical thing. It's a bit like smell. but much more limited range. It's again vibrations. And when we come to touch, there's different vibratory rates that are transmitted to the brain based on the type of thing that's being touched. There's a difference between tickling you with a finger, with a feather, poking you with a sharp point, or hitting you with a blunt instrument. And there's thousands of different types of feelings we have based on the different sort of frequencies that are being sent. So all of these, so when we think about cycles, oscillations, the sensors are all based on these things that are giving us information about the world around us.
Yes.
It's a very incomplete set of information in that we've seen that with the sensors that we've got. There are often things far beyond that we don't pick up. Sometimes different animals pick up slightly different ranges of sounds or of light, the different ones.
Colours.
But the particular part that it's used for the colours, it's the range where the most energy is coming from the sun, and so it's a good one that you can see easily all the time when the sun's up and a bit when the moon's up. So those are the inputs that we've got,
Yes.
which are just a fraction of what's around us. We've made instruments to pick up more of those ones and to pick up different things like the magnetic field, which there's debate. Some animals have got sensors for magnetic field. And
Birds in flight, for instance.
Ones that travel long distances. And there's been some experiments that hint that humans may have some sort of a little bit of a thing on that as well. And so we may, in fact, there's lists of things where people say, no, it's not 5 sensors, there's actually a few more that we can do under various
Indeed.
things that are, but they're a bit subtle and they're not always working. So we can include all those,
Yep.
but we're still missing a lot of what happens in the world. So our view of the world has come through a lot of filters.
Yes.
When we want to think about what's going on in the universe, when we try to understand the physics of the universe, the nature of the universe at a deep level, and how that then comes to us, it's important to understand one thing. In physics, they'll often talk about electromagnetism being linear. Now, I need to explain what linear is and what non-linear is. If we have, say, a pond, and we drop a stone in, and we see a circular wave go out,
Yes.
and we drop another stone somewhere else, a circular wave goes out, we'll see them travelling through each other, seemingly without interaction. The waves will be higher where the two waves are crossing, but it travels on, and the wave that went from one will arrive somewhere else, and the wave that went from that will arrive somewhere else, seemingly unperturbed. But in actual fact, there's a tiny bit of interaction there because the speed at which a wave travels depends on the depth of the water. And that's the reason when we get near a beach, we see a wave coming in, a wave that's doing a nice just rolling thing like this. When it gets near the beach, it suddenly rises up and breaks.
Yes.
The reason is that it travels faster where the water's deeper. And the water's deeper at the peak of the wave, and it overtakes the trough. It actually gets right over the top of it and crashes. So that's an example of non-linear behaviour in a wave. It's not, 1 and 1 doesn't make 2, it can make something other than 2.
Yes.
When we add 2 waves together travelling in different directions.
Yes. Well, for 2 traveling waves that pass through each other, that is a very minuscule effect.
Yes. In most cases, that's so. If we consider light that we go out on a starry night and look at a star that's light years away, that's travelled this phenomenal distance. It's taken it 4 years at the speed of light to get here from the nearest star.
Yeah.
And we see it, and it looks like it just comes from that point, and it does. But at the same time, someone else standing over there can be looking through the same path and seeing the light of another star, and someone else here can see. They're all travelling through every point. Every point has got the light of every star travelling through it.
Yes.
And they're all doing it seemingly without interaction because they're all arriving at their destinations. And to understand how that can be and why that's the reason physicists say that light is linear, because they go through like that. But I'll give you the reason why I say it's non-linear. If it was linear, that light would have gone straight out the back of our head. There would be no interaction with our body.
Like 2 stones in a pond.
Yeah, right through. So if the fact is the light doesn't go out the back of our head, it interacts in our eye.
Yeah.
Interaction if we look up the meaning of linear and non-linear and
Yes.
the meaning of interaction and no interaction,
Yes.
we find they're a perfect match. If you have interaction, it's non-linear. Right? That's what it means.
That's what it means.
Yeah. And so we can say light is definitely non-linear. In the case of that light travelling from the stars, we have to think about what happened. It started at a minuscule point at some atomic structure changing at one atom or one molecule, and some light went out from there, and it spread out over a sphere that got bigger and bigger until it reaches here. The sphere is phenomenally big compared to the size of the original atom.
Yeah.
And so that's the energy of that photon that was emitted has spread over that huge area, which means our chances of actually seeing one photon is phenomenally small. But fortunately, there's enough of them that will pick up some.
Yeah.
But we have to understand that energy being so diffuse, when we talk about adding them, we're adding 0.0000001 when the light goes through another one to 0.00001 or 2 or something else. We're adding those together. When we've got a nonlinear relationship, there's a curve, but we're adding things at such a tiny end. For all intents and purposes, it's linear there. We would have to measure the intensity of the light to 20, 30, 40 decimal places before we could detect the nonlinearity. And we don't measure it to that accuracy. We can't measure anything that accurately.
No.
So therefore, it appears to be linear. But when it goes into our eye, an entirely different thing happens now. Now we're getting interaction between this very weak wave and the atoms in our eye, which are very condensed wave structures of electromagnetism, in my view. That's not a totally widely accepted thing, but I think that if the physicists suspend their disbelief on that for a while, they'll find a lot of other things work. And we talked about the wave structure of matter and so on.
Yes.
So, but at the very least, they will agree that the energy density of the matter in our eye is much greater than the energy density of a light wave travelling in space. And so when that comes into contact with that, we see all sorts of things. We get refraction. Refraction is an interaction. When the light hits the surface of the lens, it bends, and that's how we get the focus. That's to concentrate the energy into a much smaller area so we can detect it. And at that point, it actually reacts on the retina of our eye, creating an event that sends some signal to our brain if it gets enough of events. So the interaction is happening. So it's important to understand that all the sensors are based on vibration of different types, and that they all work through nonlinear interactions of the signal that is coming and our sense organs. So once we understand that, we can begin to think about some other aspects of what nonlinearity means. In the harmonics theory, I suggest that the fundamental equations of the universe are nonlinear. If they weren't, we wouldn't observe the universe. I'm going to suggest that there is one single simple set of equations for the universe, something very similar to Maxwell's equations, and it just requires a little bit of additional understanding of Maxwell's equations to say that that matter is a type of electromagnetic standing wave. Once we understand that, we can begin to do it. Now, I arrived at that idea because the harmonics theory predicted, from the size of the largest things in the universe down, it predicts all the strong structures that we observe in the universe, and the atomic and the subatomic scale are predicted by that. And so I understood that those scales, atoms and subatomic particles, are standing waves of electromagnetism.
You got the distances of the galaxies.
Yeah.
Right
stars,
down.
the planets, moons.
Fine-tune the Hubble constant, and so forth.
So that's the logic of that. I prefer, rather than to use Maxwell's equations, some people at the time used to, before that and after that, used to talk about the ether. And my preferred explanation is in terms of the ether. what do we mean by the ether? Now, there's several different forms of ether that are proposed at different times. Some of them talk about a fluid, and some talk about a tensile ether. My preferred form is that it's a tensile ether. And the way we can think about that is most easily understood as something like a bowl of jelly, which you call jello, and we're going to get confused about jelly and jam and jelly and jello, but we're talking about that stuff you have in a bowl that you eat,
Yeah.
and it wobbles around if you move it. It's easy to understand what's happening in this as a medium in which waves travel. If we get that and we give a little prod somewhere, we'll see little waves travelling out from that. But we can see with this, if we give it twists and things, it's a tensile medium. If we give it a twist and let it go, we'll see waves that are going, making shapes like this in these, and doing this and wobbling. That's the sort of waves that I think matter is made of. And we will use particular reference, say, to the work of Milo Wolf, who showed that with these equations he can explain exactly the properties of an electron from an ether.
So a standing wave is contained, like a drop in a teacup.
Yeah.
But a drop in a pond, as just an example,
Yeah,
traveling.
It's a travelling wave.
That's a traveling wave.
Yeah, but the thing that contains the standing wave of a particle is the universe.
Okay.
And so that seems a bit funny because it's got to bounce back from there. It's going to take a long time, and it might have moved by then. So we'll come back to that later.
Okay.
And that's the quandary. I think that means that physicists don't take it seriously, but it's to understand that the universe itself is making these wave structures that do converge on points, and that they do have a stability because although other things move and cause the refraction of the energy coming into that to move about, so that we've got things that are coherently moving, like our hands and our bits and pieces, they are. It seems like it would have to be very contrived to keep on making things, but it does what it does, and we interpret it as a thing, whereas it's actually a stream of energy arriving at those places. Now, to give an example of something that's a little bit like that, we watch a TV set. When we watch TV, we see people moving about and so on. And our mind makes a picture of the people moving about.
Yes.
But in actual fact, there is no person moving about.
No.
There's a stream of light arriving on the surface that's coming off the surface into our eyes, and we see the pattern of the movement. And I'm going to suggest that all the stuff we see is that same type of thing. It's a three-dimensional equivalent, but it's people often talk in terms of this sort of thing being a holograph, right? And that's what it is. It's not the deepest level of the universe. The deepest level of the universe is the ether underneath, and all that we see are standing waves in that, energy converging on points and so on, that make the appearance of things. Now, we've had ancient philosophers talk about that, Plato's cave and all sort of things, and
The substratum
and
of
Buddha
the
and
universe.
these other ones. Yeah,
From the
these have
unmanifest comes the manifest.
Yeah, so those things have been talked about from ancient times.
Yes.
I'm trying to give a means to understand that by the wave structures and so on, how these wave structures in the ether lead us to see all these things in the way that we do.
And we have a tensile medium. The ether does exist to allow this to travel.
Yeah, and the reason some people think it can be a fluid medium, not a tensile medium. My preferred reason for thinking it's a tensile medium is that light is a transverse wave. When light travels from here to here, it's not like sound. Sound, it's bumping against the next molecule all the way along and making this pressure wave. Light doesn't travel that way. Light's more like a tight string, and you give it a wobble and it does a thing like that along it, right?
Yeah.
And it's the tension in it that causes the wave to travel like that. Now, you can have pressure things in the ether as well, but it's whether it's incompressible, I don't know. It's probably not highly compressible. So what we see with water, it's fairly incompressible compared to air. So when we make waves in water, it has to get out of the way. You know, you can have a tiny bit of compression, but not much. The ether's probably like that, but it's got the tension that the water doesn't have. It's more like a solid thing. If we get a big blob of steel and we whack it with a hammer, all these vibrations will go on. That's what the ether's like, and the initial vibration is the size of the thing. So it is contained in that, and the vibrations in there stay within that. But it's a huge thing. It's the universe. It's and it's much bigger than the Big Bang people think it is. It's about 10 million times larger than that. Than the size that they can see. Actually, strictly speaking, they don't say it has that size. They say it's at least that size.
Yeah.
It can be beyond the stuff
Beyond the
horizon.
observable universe.
So they talk, if we use the words observable universe, we'll keep that straight. I shouldn't accuse them of things they haven't done, just the things they have.
Yes.
Yeah. Okay, so that's the senses and the vibrations and the nature of the universe as being an ether.